So today, we begin our last statistical test of the semester, the correlation and regression analysis. And you might find that you already know a lot about correlations and regressions because it's something that you probably learned about in high school. And it's probably things you've utilized in college and things that you see all the time on news reports. Correlations are very common, very popular, and they can tell really interesting stories. So we are going to learn how to actually calculate the correlation and regression statistics and learn about how to actually analyze and interpret the results that we get. We are mostly going to use the R built-in functions for correlation and regression. I will introduce some of the equations, but we are going to use the built-in functions because the calculations for correlations and for regressions can get a little bit out of hand. So before this point, we've been using statistics to compare groups of observations. And determining the probability that the differences seen between those groups is not due to random chance. So if we see differences in means of two samples, does it actually mean that they're from two separate populations? However, the real strength of statistics is not just the comparison of samples, but to predict future observations. And we do that through correlation and regression. A correlation, by definition, is the determination about how well we can predict some variable y, or the dependent variable, from some given x, which is the independent variable. In this case, both y and x are numeric. The parameter for a correlation is rho, and the estimate is r. A regression, on the other hand, is how well the expectation of y changes with changes in x. The parameter for regression is beta, and the estimate is b. Let's take a look at an example of some hypothetical data. And it's going to be two graphs, so first I'm going to run parm_rho. Then I'm going to make two hypothetical data sets, x1 and x2. So x1 is a random sequence of numbers between -3 and 3. And then y1 is a sequence of numbers between 13 and 19. Here we need to make sure that our observations of y and x are the same length so that each y is associated with a particular x. So let's plot these and see what it looks like. Then we can see, so here x is on the x-axis and y is on the y-axis. You can see is that the points make a very tight line. And it looks like as x increases, y also increases at the same rate. And we would say that the correlation is high, or the R is high. In this case, the correlation is perfect, so in fact R equals 1. We can also put a line of best fit, or a regression line, and you can see that the line hits every single point evenly. So this is a really good correlation. So let's take a look at a correlation that isn't so great. So here is another x2, which is the same sequence of numbers, -3 to 3, but then I just put a bunch of random numbers for y2. Run that, take a look at that plot. See, these points are more scattered. They don't make a really nice line. We can overlay a line on it, and it sort of looks like a line, but as you can see, some of the points are farther away from the line and some are closer. And so the relationship between the points, and therefore the relationship between x and y, is not very strong. Here, r would be pretty small. We wouldn't have a very good correlation. The next question is there a significant correlation between any given set of data? And that's where correlation analysis comes in. Correlations work by measuring what's called covariance. And covariance is how two measurements from the same subject deviate together from their means. And so how does each observation of x and y deviate with each other? And the equation for sample covariance is the sum of xi minus x bar times yi minus y bar, all divided by n minus 1. R describes how reliably x and y change together, and R is called the correlation coefficient. If you remember, R is the estimate of the parameter rho. And I'll have this equation pop up here. This equation you do not need to memorize, but as you can see, it's quite complicated, and it takes into account the covariance between x and y. A parameter called r squared describes the amount of variation in one variable that can be predicted from the other variable. And this is very similar to an F statistic, except for it is 1 minus the mean square error divided by the mean squared total. So what r squared tells us, and we talked about r squared a little bit with ANOVA, it tells us the amount of variation explained by differences in our data. However, you can ignore these equations because they are built into R, and instead we're going to focus on using the correlation function and interpreting the results.